Okay, so solving systems of equations. So this is what these objectives are what the SOL tells us we're supposed to get out of Algebra 2. Everything that we're really supposed to be doing at this level is nonlinear systems. That's why that extra credit stuff was to, copy. What are the possibilities, right? If you have a parabola, right? If I have a parabola and a straight line, that would be a linear quadratic system. In how many different ways can they intersect, right? You can get two solutions, you can get one solution, you could get no solutions. Am I still frozen? Sorry. Right. So is there any way to get more than two solutions to a linear quadratic? No, the most you could get is two. How about a quadratic system? Well, here's the thing. Up till now, you've always thought, well, quadratic means that. But actually, circles are quadratics, ellipses are quadratics, and hyperbolas are quadratics. So when you start talking about all the different ways that those shapes can intersect, what if I have a hyperbola and I intersect it with a circle, I could get 4 solutions, up to 4. So, you could play with those shapes, and that's kind of what those drawings were, but you could get up to 4 solutions. There's no way you'll ever get more than 4, but you could get 4 solutions out of this. You could also get, 3 or 2 or 1, any number of them. Usually on the SOL, there's probably going to be one question which says, like, it's a picture, and it's, like the things you just drew, and it just says how many solutions are there. And so you're just supposed to look for all the intersection points. That's it. So that is honestly the things that we're supposed to be doing in Algebra 2. But how many of you remember systems from Algebra 1? Really, really well. You want to be tested on that right now. That's how we're going to go back and do that part of it. We won't spend as much time as you did in Algebra 1, but we are going to take a day or two to do the things that you did in Algebra 1 with systems. And that means that it's going to give us it'll be a 4-lesson unit. Right? The first day we're going to remind ourselves about systems and do substitution. The next day we'll do elimination. All of this with linear systems. And then we're going to do graphing. And by graphing, we're going to go back and learn how we graph them with the calculator. So that then we can use all of that stuff to do the nonlinear system. So it ends up being 4 days. So systems of equations. More than one equation with more than one variable, that's what a system is. It's usually if you've got the same number of variables as you do equations. And if it's a linear system, then you should be able to solve for it. So you're usually talking about 2 by 2, 3 by 3, 4 by 4, something like that. Right? The solution to the system is all the points that satisfy all the equations. For what we're doing here with the linear, then if you can graph them and there's an intersection point, okay, then it's just 1. But when you get into these nonlinear, then you got more possibilities. Could be 2, could be 3, could be 4. Okay. And let's see. The thing about systems of equations is that you're going to get asked about these things in the course of being asked about other things. And it doesn't say anything like, here's a system of equations. It just becomes part of it. If there's 2 unknowns, then you need 2 equations. So it just becomes kind of natural. We see this a little bit like in this class and then maybe in the next class. In calculus, you see it all the time. That there's 2 things that are being asked for, so you got to know, oh, well, that means I need to have 2 equations so that I can solve for it. I think I'll leave that part out of it. Do you remember when we watched the movie, The Great Math Mystery? And they did Maxwell's equations. That was the thing that, predicted the electromagnetic waves that did the radio first and Marconi, and now they do our cell phones and all that. Well, Maxwell's equations are 4 equations with variables, kind of, vectors and things like that we wouldn't get, but still, it's a system of equations to get solved. In meteorology, like what I used to do, what we call the primitive equations that are used to forecast the weather. When you watch the weather on TV, they're all using these same basic, same basic models that start with these primitive equations, and they are 7 equations and 7 variables, right? And the variables are pressure, temperature, humidity, wind, but wind is 3 variables. There's the east-west component, there's the north-south component, and there's the vertical component. So that's 3. Now we're up to 6. And then there's a variable for condensation, which allows moisture to come out of the atmosphere. So you can, by going upward vertical motions, you can make water vapor condense into cloud drops, condense into water drops, but then somehow it's got to fall out. So now, if it was 7 equations and 7 variables, and they were linear equations, that means you just have one answer, which wouldn't be very interesting for the weather. But these aren't linear equations. They're partial differential equations in time as an independent variable. So, basically you start them out and then you watch them march forward in time. But it's systems. And it all starts with just this stuff right here. Let's see. So 3 possibilities for a 2x2 system. Right? First one. I got that. Can't see what color that is. So let me draw one line. 1, 2, 3. And I'll draw another line. Okay, if the 2 lines have different slopes, then they will intersect at one point. If the 2 lines have the same slope, but they have different y-intercepts, what do you call that? They're parallel lines, right? So parallel lines, a system of equations whose graphs are parallel lines, means there's no solutions because the lines never cross. Right? So that means they've got the same slope but different y-intercepts. Now, what kind of lines would you have if they had the same slope and the same y-intercept? It would be the same line, right? It's basically one line right on top of the other. And so how many points do they share? Infinitely many points. Right, so we spend most of our time trying to figure that one point. Where do they intersect? Okay. Good. So here's our methods for solving linear systems. Graphing, substitution, elimination, and then one more that we won't cover here, but it's matrices. Personally I like to solve with matrices, but matrices used to be part of this class, part of Algebra 2, but it was taken out of the SOLs. I think when they did the 2009 rewrites of the SOLs, they took matrices out of there. And, matrices, that's plural for matrix. And, basically you learn how you can solve equations like 2x plus 3y equals 4 and 5x plus 6y equals 7, for example, by turning this into a matrix equation. 2, 3, 5, 6 times xy equals 4, 7. And all this is easily entered into the calculator as matrix. And then you solve by just doing a to the minus 1b. First you have to understand about matrices, you have to understand about matrix multiplication, inverses of matrices, but in the end, that's kind of what you do. You know what I mean? It's more of just a mechanical process. Okay. So what we're gonna do is first we're gonna look at graphing a little bit today. Then we're gonna do the substitution. Then we're gonna do the elimination, and then we're gonna go back to the graphing, and we're gonna show how you do it in the calculator, so that you actually don't have to your answer doesn't have to depend on your ability to draw an accurate graph. It's actually the calculator does it for you. So solve by graphing. So if I have to graph these two lines, and both of those lines are in standard form, I think that probably 95% of students at this level, you're going to say, well, I'm going to solve for y. I got to put it in slope-intercept form and then graph it in slope-intercept, which is fine. You can do that. In fact, when we graph with the calculator, we'll have to do that because you got to solve for y, so you can hit the y equals button and put it there. But not with a calculator. In standard form, you can plot, and I would always. I wouldn't solve these for y. I would find the x and the y-intercept and then connect those 2 points. Right? You just need 2 points for a line. How do you find the x-intercept of a function? Yeah. Yep. You substitute y equals 0. Okay, but if you substitute y equals 0 here, that whole term goes away. So really all I'm going to do on my screen, I'm going to use my whole hand and cover it up. On your paper, you just use a finger and cover it up. And then what's left? 4x equals 8. So what is the x-intercept? It's 2. So I'm going to plot a point right there. Okay, then I'm going to solve for the y-intercept, which means substitute x equals 0. What is the y-intercept? It's 8, right? So that to me is much easier than having to solve for y and then graph it like a slope-intercept form. But what's the x-intercept of this one? 9, right? 2x equals 18, so x equals 9. What's the y-intercept? -6, right? So 18 divided by -3. So you plot those 2 points, done. So you don't have to really take that step of putting it in slope-intercept form. But if you do, then it should look like this. Y equals -4x plus 8. And y equals, if I move the negative, make that a -2x on the right, then I divide by -3, then I'm going to get 2/3 x minus 6. Right now, if that's going to be your method of doing it, then at least you got to know how to graph a linear equation that's in slope-intercept form, right? What's the first step? Like I'm going to do this y equals -4x plus 8. What do I graph first? The y-intercept is -8, which is a little above my graph. Okay, then how do I use the slope to find another point on that graph? Yeah, you use the slope, right? Down 4, right 1. Down 4, right 1. Okay, with those 2 points, I know where this line is. So let me... Close enough. Okay, now let's go back. This one has a y-intercept of -6, so I'll go down 6. And the slope of 2/3, so up 2, right 3. It doesn't seem right, but probably is. Draw a line. That looks pretty good. Okay, so do we see a solution? Remember, what are you looking for a solution? The intersection point. So do you see an intersection point? I mean, yes, you do. You see an intersection point right there. Okay, so then you got to estimate what are the coordinates of that point. And if I'm looking at the point, as it's drawn, I mean, it looks like it's a little bit more than 3 and a little bit less than -4. Again, that's only as accurate as my graph. I think when I did this in 1A, it actually landed exactly there. So it could be this line right here, the blue line. You know, maybe I missed that point by just a little there, and that kind of leads to it being a little off. So I'm gonna estimate that this solution is 3, -4. So you look at the graph and you estimate 3, -4. How can I confirm if that's the answer? Substitute it in the equations and see if you get the right answer. So do we? 4 times 3 is 12, -4 is 8. That's good. 2 times 3 is 6, -3 times -4, that's like 6 plus 12, which is 18. So actually that checks out. Right. So that's solving by graphing. Okay. So try to do the same thing with that one. Okay. So I'm going to do it by doing the intercepts. So on that one, looks like the x-intercept is going to be -10 divided by 4, which is -2.5. So there's -2.5, 0. And the y-intercept is going to be -10 divided by -5, which is 2. So there's those 2 points, -2.5 and 2. And draw a line. Pretty close. Okay, then we'll go back, and in red, I'm going to do these. What is the x-intercept? 4 divided by 2 is 2. So 2, 0. And the y-intercept should be 4 divided by -7, which is -4/7. So here's these 2 points, 2, 0, and -0, -4/7, which should be just between 0 and -1, closer to the -1. Draw a line. That's my guesstimate of it. So do we see the intersection point? Somewhere around there. So estimate that point. -5, -2. So now I got to plug it. Let's make sure that's correct. 4 times -5 is -20. -5 times -2 is +10, which is -10. 2 times -5 is -10. -7 times -2, which would be like +14. So -10 plus 14 is 4. So they both check. So that is the answer. Right, so then we get on to something that will actually solve exactly, so we don't have to depend on our graphing skills. Substitution. Right, these are the steps. I think you copied something in the extra credit homework, but this is my wording of it right there. So first, we solve one equation for one variable. We substitute for that variable in the other equation. Right? By doing that, we reduce that other equation to just one equation and one variable, which we can solve for rather easily. Right? Then with that one variable, that's one coordinate of an ordered pair, we've got to find the other coordinate. So we go back to that equation that we solved in the first step and plug the answer we got in the second step, and that's how you find the other coordinate. We'll practice it a couple times and you'll see. Right, the solution is a point, x, y. So solve by substitution. First step, solve one of those equations for one of those variables. Right? You can solve for either variable in either equation and be right. But sometimes there's an obvious choice. In this problem, what would be the obvious choice of the variable to solve for? The second equation for which variable? For x. Right? You definitely want to, if you can, choose a variable which has got a 1 as a coefficient. Because if you don't, that means in the last step of solving, you're going to be making fractions. You still get the same answer, but it's harder to work with fractions than not. So definitely try to choose something which is easiest to solve. So if I solve this one for x, I get x equals 3 minus 3y. Or negative 3y plus 3, it doesn't matter. That's the first step. Okay. Second step, substitute for that variable in the other equation. So we want to put it into the x right there. 2 times 3 minus 3y plus 5y equals negative 5. So by doing that now, we just have one equation and one variable. And that we can solve with a linear system. You know, it's going to be basic algebra 1 kind of isolating a variable. So let me distribute. Combine like terms. Subtract 6. Multiply by negative 1. Right, that's the end of the second step. Okay, then substitute that answer into the equation you solved at the end in step 1, meaning here. That's the perfect place. If you want to find the x, plug it in there. X equals 3 minus 3 times 11. X equals 3 minus 33. So x equals negative 30. So what is the solution to this system? Negative 30, comma 11. 10. You could check it by plugging it in, right? 2 times negative 30 is negative 60, plus 55 is negative 5. Negative 30 plus 3 times 30, negative 30 plus 33 is 3. So that checks. So try that one. I would have definitely gone this way. 3x equals 6y plus 9, which means x equals 2y plus 3. Now I substitute in the other equation. Negative 4 times 2y plus 3 plus 7y equals negative 16. Negative 8y minus 12 plus 7y equals negative 16. Combine like terms. Negative y minus 12 equals negative 16. Add 12. Negative y equals negative 4. So y equals 4. Right, and then where do I go to find the other coordinate? Right, you go back up to that equation, the thing that was the result of step 1. X equals 2 times 4 plus 3. So the solution is the point, 11, 4. Okay, solve by substitution. So which one of these would be the easiest to solve for the variable? Probably the top one for x, right? So x equals 2y plus 4. So I should substitute for that variable in the other equation. 3 times, come on, what happened? Sometimes this happens. 3 times 2y plus 4 minus 6y equals 8. So we get 6y plus 12 minus 6y equals 8. 6y minus 6y cancels, so we have 12 equals 8. What does that tell you? Tells you there's no solution, right? Because there's no variables involved. That means it doesn't depend on the variables. It's either always true or always false. This is false. So that tells you that it must be always false, which means no solution. And what does that look like on the graph? They're parallel lines. So if you solve something like this and you get all the way down to that point right there, you got to say what it means, right? You got to say that means it's parallel lines. Okay, next one. Solve by substitution. Okay, I'm going to solve the second one for y. Y equals 4x plus 3. So 12x minus 3 times 4x plus 3 equals negative 9. 12x minus 12x minus 9 equals negative 9. So these cancel. And so we get negative 9 equals negative 9. What property says that's true? Reflexive property, right? So that is true. So what it means is there's no variables involved. It's either always true or always false. In this case, it's true. So what does that mean in terms of the graph? It's the same line. I don't know how they show the answers in the back of the book for this. Sometimes in these textbooks, when they get a same line situation, what they'll do is they'll set it, they might use like this set bracket and say like this, the set of all x, y, and then you use this vertical line, you read that like such that, and they're of this form, x, 4x plus 3. That means that that's the set of all the points that are, for any value of x, the y value is 4x plus 3. If that's what that says right there. So I wouldn't be surprised by that, but I'm not really sure how they do it in this book. So try that one. Same line. So which one did you solve?
I solved for the x value in the first degree.
Okay, so what did you get?
X equals negative, or y plus 5.
Plus 5, plus 4. 20 over 5 is 4. So I mean, I solved this one here for x. In a way, I mean, I could like add this and then multiply by negative 1. In my mind, I moved that over there and I moved that over there, and I got that. And then I substitute this here. And then do the math. I got 20 equals 20. Same line. So try that one. Low line. You know, exactly what you show right here depends on which one you solved. But I solved the top one for x. And I got x equals negative 5 halves y minus 2. And I substituted that in. And the 5 y's canceled. And 4 equals 9 is false. So that means no solution, parallel line. Okay. So that is that. Kind of like it's a refresher about what systems are. and the process of substitution.